Okay, hi everyone. It's week 5. Hope you guys had a good break last week from the public holiday. But let's begin with our next topic. Today we'll be talking about randomized algorithms, and so it's a bit of a shift. So the first 3 weeks we are talking about basics in 3230. Then now we're gonna shift towards this paradigm of randomized algorithms. Okay, I think it's a very exciting chapter in general, and so let's talk about it. Okay. So why do we want randomization? Okay, so the thing about randomization is that it allows us to guard against worst cases, and the famous example is things like quicksort, right? So we don't want an adversary to come up with an input that runs in O(n)². If you have the naive quicksort, the deterministic version, the adversary can always like set up some input such that it's gonna perform badly, right? Like maybe if you keep choosing the first element as pivot, then you keep giving it an input that is reverse sorted. Okay, so we want to guard against worst cases like that. Performance, randomized algorithms actually can be very, very performant. In some cases, there are problems, right, that actually can only run in exponential time if you solve it deterministically, or at least we don't know a better solution. But with randomized algorithms, with some trade-off in accuracy of answer, you can bring it down to linear time. Okay, I think that's pretty cool. So simplicity also. Most randomized algorithms are very simple. It's most of the time it's just like flip a coin or like randomly choose something, and then suddenly you get pretty good results. Like you don't have to understand these examples here. It's from a module I took in the past, like last semester. But like from here, I hope you can see that the randomized algorithms tend to be very simple. Like here, you just have a sum counter, and then you just choose a random index and then sum the element in the index, and suddenly it gives us like an answer that is reasonable. I mean, you have to prove it, but I can guarantee it's pretty reasonable. Okay, so sometimes we also want to do better than the deterministic lower bounds. Okay, because some problems have a deterministic lower bound of like omega n. So sometimes if you allow randomization, you can actually beat this lower bound to some extent of tolerable error. Okay, so this is just like some motivations why we want randomization, why we are dedicating part of 3230 just to talk about randomized algorithms. Okay, so for the first question, we have about worst cases. Okay, so the story is like this, like like maybe some of you have not prepared to answer questions in class, right? So let's say this Christian over here, he comes up with an algorithm, and I want to choose K of you. Okay, I want to choose K of you. So in the worst case, right, because I want to identify those of you who haven't done the tutorial questions. Don't worry, I won't point you out here, but like I want to find out people who have not prepared. Okay, but to me, the worst case is that if I choose K of you, then exactly K of you are the only ones who are prepared. Like basically everyone else got very lucky. It was safe, like the remaining of you didn't prepare, and you were safe because you are not part of the K that I chose. So let's say I tell you my algorithm, right? Like I make it like open source, So can you guys force this worst case to happen? Like, can you guys collaborate and like actually ensure that I am not able to identify those of you who did not prepare? Okay, so I hope the question is clear. So I'm just gonna like because this is a pretty like short question. Like, can you guys just go to Archipelago and like tell me what you think, like whether you think you're able to force this worst case to happen or not? If the question is not clear, please let me know. Okay. So in the meantime, maybe I'll just like re-elaborate. So I say I have 5 students, right? Then let's say K2 prepared, 3 did not. Okay, so like let's say I have an algorithm that chooses 2 people, choose 2. Can you guys, like, if I tell you my algorithm, can you guys ensure that the guys who prepared are the ones that I chose, to always allow this to happen? Okay, so that's the question. Okay, so I'll go on. So surprisingly, it's no. The answer is no, because I just can come up with a simple randomized algorithm. So I just choose K of you randomly. Okay, and the thing about randomization, right? If I choose K of you randomly, you guys won't even know who's going to be chosen by this randomization. Like I won't even know which k numbers will be chosen from 1 to n. Okay, and because of this, right, like there's no way you guys can always at all times guarantee that you guys are safe, in the sense that only the k people who have prepared are the ones who are always chosen in this algorithm. Okay, so again, like here, if your algorithm makes use of randomness to make decisions, even like those of you guys, myself included, knowing the algorithm cannot find out a way to force the worst case to happen. Okay, so I hope that is like makes intuitive sense. First time I attempted this question, I also thought like, yeah, of course you can always force it to happen, but then I saw the answers and it was no. Okay, so this is just like, again, motivating randomization, right? Like a way that we can ensure that we don't force, like no one can force the worst case. Okay, so that's a simple warm-up question. So next up, so random, yep. Is it true that, okay, there's a question in the chat. Is it true that for every deterministic algorithm, we can find the worst case? Okay, I can't like say 100% with 100% certainty that it is always. I tend towards yes, we can find the worst case if it's a deterministic algorithm, but yeah, I'm not 100% certain on that. But for randomization, at least like there's no way we can force out the worst case at all times. Yeah. All right. Okay. So the next part, I'm not 100% sure if this was covered in lecture, because as I remember, this tutorial is typically like self-contained. So if these are not familiar terms to you, please do pay attention. So let's talk about random variables first. So random variable, let's call it x, is a function. Okay, it's not exactly a variable that will map a sample space to a real number. Okay, so let's say like x be the random variable of the number of hits in 2 flips, right? Like you make 2 coin flips and how many hits are there? So this is a sample space, HH, HT, TH, TT, right? All the 4 possible coin flips. So can think of it this way, like you give this something from the sample space to the random variable, and it will spew out an output. Okay, it tells you, oh, okay, from this input, there are 2 hits. Okay, so typically like we can write it like this. So x is 2 with probability a quarter, right? Because you know there's only one such cases where it's both hits, and then 1 with probability half, because this is the h hit tails and tails hit case, and 0 with probability a quarter. It's tails tails. So this is a random variable. It simply takes in an input and output a real number with some probability. Okay, so typically the sample is random, right? So it's with some probability you output a certain number. Okay, this random variable. We can also write it like this: PR, like probability of x equals to 2 equals a quarter. Okay, you'll see this a lot. So now let's talk about, shift a bit to something we call the Bernoulli trial. Okay, so in instance of Bernoulli trial, yes, a probability P of success and probability Q of 1 minus P of failure. Okay, Q, let's say. So it's kind of like a generalized coin flip if you think about it, because a coin flip is success with probability half, then fail with probability half. So maybe, for example, right, like I can define my own success, right? So I define success as getting 6 when I roll a die. Okay, so this is a Bernoulli trial with P, the probability of success is 1/6. And probability of failure is 5/6, because if I roll any of 1, 2, 3, 4, 5, that's a failure to me. Okay, so all right, so this Bernoulli trial, there's going to be a lot of terms like new, maybe new terms to you today, but hopefully if there's any confusing things, ask me to repeat. Okay, so the next thing we talk about is geometric distribution. So it's a sequence of independent Bernoulli trials, and each of them, and this is important, each of them must have the same probability P. Like you repeat the trial over and over again, repeat the same trial. Okay, so let x be the random variable. So x is the random variable for the number of trials needed to obtain success for the first time. Okay, intuitively, this is like you keep trying until you get it. Like you're very stubborn, you know, roll a dice until you get 6. Okay, so you keep trying and roll and roll and roll, and let x be this random variable of how many times do you need until you roll 6 for the first time. Okay, so if you roll 1, that's a failure. Roll 2, that's a failure. Roll 1 again, that's a failure. Then you get 6. Then that means there are 4 trials in order for you to get 6. Okay, so if X is this like property over here, like it's counting the number of trials before succeeding for the first time, then we say that X follows the geometric distribution, okay? And probability of X equals to K, like K is the number of trials needed, is like if you succeed on the Kth try, right? It must mean that you have failed K minus 1 times, right? Because we're tracking how many times do we need before we succeed for the first time. So we failed K minus 1 times the probability of success just that single one last time. Okay. Then I hope you remember expected value. So it's like the weighted average probability times the value. So the expectation of X is simply 1 over P. And I won't derive this in class, but just remember this, okay? So expected of geometric distribution is 1 over P. I guess intuitively, if you think about it, if you have six dice, if you want to roll until you get 6, right? Maybe because probability is 1 over 6, so you expect it to like fail maybe 5 times until you get it for the first time on the 6th try. I guess intuitively, if you like, that's how you can think about it. Okay, but I won't derive this in class, just remember this, 1 over P. Okay, so let's say, for example, like let X be the random variable for the number of trials to reach hit for the first time. What is the expected value of X? First of all, this is a Bernoulli trial with probability of success half. So expectation of X is simply 1 over half, which is 2. Okay, simple math. This is just using this fact. And again, like as I mentioned earlier, dice roll. So let Y be the random variable for how many trials you need to roll a 2 for the first time. As I mentioned before, this is a Bernoulli trial with P equals to 1 over 6. So the expected value of Y, like how many trials you need, is 6. Okay. So I hope this is kind of like simple enough. And this will be used like for the next question. Okay. So here, like again, like I'm stubborn, like finding unprepared students, right? So I'm very committed to finding people who hasn't prepared. So let's say I choose students at random, okay? And I want you to take note, specific for this question, is just to motivate geometric distribution and so on. This is a with replacement, okay? So meaning like, let's say I choose like one student, one of you, okay? I choose student A. Then next time I do randomization, I will again possibly choose that student A. Okay, I know if you do it without replacement, eventually I'm gonna hit someone who has not prepared. But in this question, just for this question, assume that I do it with replacement. So potentially I ask someone who has prepared, like the same person. Okay, so the question says that I keep repeating until I find someone who has not prepared. Okay, so let's say, right, I have n students and k of you have not prepared. Okay, like k of you have not prepared. So how many questions should I prepare in expectation? Like how many times do I need to try asking a question until I find someone who has not prepared? So let's say these 3 people have not prepared and there are 8 students in total, right? So how many times do I need? Okay, before like I sample randomly until I hit one of these 3 people. Okay, so again, take some time to think about it and fill in archipelago. Okay, is the question clear? Okay, if no one's asking anything, I'll presume it's clear. Let's resume at like 11:17. Okay. Okay, I think I'll just resume. Okay, it's 11:17 as well. So most of you got it right. A couple of you chose a different answer, but let's go through it, right? So again, this is exactly a geometric distribution because I keep trying until I find the first person who has not prepared. Okay, so let X be this random variable on the number of trials I needed until the first unprepared student. So the first step is for you to think about the Bernoulli trial, right? Like, what's the probability of success? So the probability of success for me is for me to choose one of the K students who have not prepared over N. Okay, K over N. And then the expected value is simply the reciprocal of this value Bernoulli trial, okay, which is N over K. Okay, so this is the answer, N over K, which most of you got it right. So for those of you who did not get this answer and you would like me to clarify, please just let me know. Okay, so this is Bernoulli trial. Hopefully this is simple enough. Sorry, this is geometric distribution, expectation of geometric distribution. Okay, so I'm gonna go on to the next segment where we introduce more concepts, but I think this should be a familiar concept to you, linearity of expectation. Okay, so for any two events, X and Y, and the events, right, interestingly, can be independent or dependent, it doesn't matter. Okay, and let's say a constant C. So we say that expectation of X plus Y is simply expectation of X plus expectation of Y. And this generalizes, right? So even if you have X plus Y plus Z, expectation of everything, you sum up everything, is the sum of its expectation. Okay, so typically I like to say like expected value of the sum is equals to the sum of the expectations. Okay, but anyway, so let's say I have a constant also, like a constant Cx. I can pull out that constant. I can pull out that constant in linearity of expectation. Okay, and I want you guys to remember this linearity of expectation is very simple, but this little hammer that we frequently use in randomized analysis. Like I think like the entire study of randomized analysis is enabled by this linearity of expectation. Okay, without this, I think we have a lot of troubles in randomized algorithms. Okay, so it's a very nice thing. Okay, so the next thing I want to talk about is this harmonic series. And I don't think Prof introduced this in lecture anywhere, but it's one of the series that I like you to remember. I think people, like students from past semester, ask me like, oh, are there more series for me to remember? Typically, I think no, aside from harmonic series and the geometric series. Typically, these are the important ones. I don't remember any other series, which is very, very crucial to remember. So, yep. So bear with me about like remembering one additional series. So if it's in this form, right, like 1 plus half plus a third plus a quarter plus all the way to 1 over n, this is summation formula. This is equals to ln n plus some constant. Okay, but what's important to us is that the harmonic series is something like theta of log n. Okay, so again, like if you see something in this form, you don't need to go compute the exact one. Just go ahead and say like, oh, it's theta log n. Okay, so harmonic series. Okay, the next thing I want to talk about is the analysis like pattern. So this is kind of like a pattern that we follow in randomized algorithms like a lot of the time. Okay, so typically when we analyze something in randomized algorithm, we try to identify a random variable where you want to count something, right? Count something, and then you express this random variable as a sum of random variables. Okay, so x is equals to like this x1 plus all the way to xn. So express it as a sum of random variables. And then, right, maybe you want to compute the relevant probability for each of this. Okay, and then you want to calculate the individual expectations of all these little things. So if you have x1, you have x2, xn, you want to compute expectation of x1 all the way and expectation of xn. Okay, so you don't compute all of these. And then what you do, right, to get expectation of x, you will make use of all these values and apply linearity of expectation. Okay, because x expands to these things. And then by linearity of expectation, the expected value of x will be the sum of all these little expected values. Okay, so it's okay if you don't fully understand this now. We're gonna keep revisiting this pattern like throughout. Okay, and well, like this is just kind of like a guiding principle in a sense. You don't have to follow these steps in any way. So again, like it's a guiding principle. So we'll try applying it to this famous problem called coupon collector. Okay, so there are n types coupons you want to collect. So we randomly draw it with replacement. Okay, again, it's with replacement. So what is the expected number of times you have to draw a coupon before having at least one of each type of coupon? Okay, so let's illustrate with examples. So I don't know if like people still play hot pals these days, but last year I think it was very hot pals, where you want to collect all these different like hot pals in Google Pay, right? You want to collect 6 different kinds of, let's say, coupons, right? Like double quote coupons. You want to collect all 6 of them. So how many times do you need to try before you can like get all these 6, right? Because after you try again, you could get a duplicate. You could get something you've already gotten, right? So what is the expected number of trials before you collect all these like hot pals? Of course, assuming they pop up with equal probability, but this is not true in real life. I think like one of it is very, very, very rare. Okay, it's a very skewed distribution, but let's say they all equal probability, right? So what's the expected number of trials before you actually get all of this? Okay, so all right, so let's now define a random variable. Let Ti be the number of trials to collect a new coupon, right? A new coupon, call it the IF coupon, after I-1 distinct coupons has been collected. Okay, I want you to like take a moment to read this definition, okay, because it's important. I'll say that again. This is the number of trials for you to collect a new coupon, okay, after I-1 distinct coupon has been collected. It is conditioned on you have collected I-1. Take note, this is not assigning an ID. So this slide, I added it because someone was confused last year. So this is not assigning an ID to each coupon and like figuring out how many times before you reach that ID. It's to find out a new coupon, the IF new coupon. Okay, so let's say, for example, here, right? So we have collected 2 coupons over here. So condition is I-1 equals to 2, right? So now we are looking at T3 because we want to find like the third new coupon. The third new coupon can be anything. It can be this one, it can be this one, or it can be this one, it can be this one, as long as it's new. Okay, it's new, conditioned on the fact that you have collected two of these. Okay, so we are interested in T3 because we want to find the third new coupon. Okay, is this definition okay? Right, anyone confused? If you're okay, please give me a thumbs up. Okay, if you're not okay, PM me, give a cross or something. Okay. Okay, good. So most of you gave me thumbs up. So I'm not gonna go on. So okay, so TI, right? So again, this is kind of like geometric distribution because the success is for you to collect the IF new coupon. Okay, the probability of success is n minus I-1 over n. And if you like, how you can think about this is that you have n things, right? You have n coupons, and you have collected I-1. So you don't really care about like these n-1 things. Like just now, I have 2 that I've collected, like 2 coupons I've collected, and I have like this thing. So n equals to 6. Okay, so the tick is like the one I've collected. So I've collected 2, and like I'm looking for I equals to 3. This is what I'm looking for, the third new coupon. So this is the probability of getting like one of these things, one of the new coupons, which is like the blue area over here, right? It's simply 6 minus the third coupon minus 1, which is 2, basically the ones I've collected, over 6. So this is this value over here. Let me know if this is confusing, but if you think about it, I think it should make a logical sense, like why this is the probability I, collecting the IF coupon. Okay, so again, this is a geometric distribution, right? This is a geometric distribution because I keep trying until I find that new coupon. Okay, so the expected value of TI is simply the reciprocal, which is like I just flip this numerator and denominator. Okay. Okay, so now our goal, remember, in coupon collector is to collect every single type of coupon. Okay, TI just tells me like the IF new coupon. So ideally, you want to collect everything. You want to consider T, total number of trials to collect all n of the coupons. So this is like this step over here. Like I put the pattern here on the upper right so that you can like compare. So you're finding the goal, which is what you want to count, which is T. You want to count the total number of trials to collect everything. So you express this as a sum of random variables, because to collect everything, you consider the trials for you to collect the first one. Then you consider the trial taken for you to collect the second one until the nth one. Okay, until the nth new coupon. Okay. Okay, so anyone confused about this formulation? I'll give it like 10 seconds, 5 to 10 seconds. Okay. If not, I'll go on. So remember, you want to find the expected value, like how many trials do you need in expectation to collect everything. So expected value of T is like simply you apply expectation of to both sides. ET equals to ET1 all the way. Okay, then this is where it's nice. You know, if you see an expectation of the sum of random variables, you think linearity of expectations. Okay, it's like this guy over here approaching linearity of expectation. Want to break this away. Okay, so you break this apart by the linearity of expectation, right? ET1 plus ET2 all the way to ETN. Okay, and this is another way you can write it. This is just using the summation notation, which can be more concise. Okay, but it's the same thing as the previous slide. Okay, this is just the summation format. So use this fact from the previous slide, right? Linearity of expectations is the summation of the expectation. Then we substitute ETI with what we computed. Remember a few slides ago, we computed specifically for TI. For TI, we computed specifically, the expectation of it is simply this value over here. Okay, this is from a few slides ago. But right now, what's important if we just substitute this over here. Okay, so with this, well, if you look at it, right, if you try to actually expand it, substitute I equals to 1, substitute I equals to 2, all the way until I equals to n, this is simply n over n plus n over n minus 1 plus all the way to n over 1. Okay, take like 5 seconds to verify that this is fine. Okay. Then I factor the n out. I factor the n out, and I also kind of like flip the order a bit. So the 1 over 1 ends up being the first term, 1 over 2 ends up being second term, and 1 over n ends up being the last term. Okay. So this, right, notice that this is the harmonic series that I told you earlier. I went through this harmonic series like a few slides ago. So if you see this pattern, right, 1 over 1 plus 1 over 2 all the way, think harmonic series. And this is exactly the harmonic series that I showed a few slides ago. It was there for a reason, right? Of course. So Hn, as I said earlier, this is theta of log n, right? This Hn is theta of log n. So the expected value of T is simply theta of n log n, where the log n comes from like the right hand side of the harmonic series. Okay. Okay, so is this question clear? Sorry, is this like derivation clear? So if there's a coupon collector problem, think of n log n. Okay, if you want to collect all n coupons. Okay, or think harmonic series if you want to derive things on coupon collector. Okay. So any questions about this? Can I get a thumbs up, because coupon collector is something we'll keep visiting for today. If you don't understand and you want me to repeat, please let me know. Okay. Okay, slightly less thumbs up now, but I hope the rest is okay with it. Okay. But okay, so the third question, right? The third question is I want to ensure every single one of you participate. Okay. Of course, if I choose like one of you linearly one by one, it's easy, but that's not fun. So let's do it with replacement. I'll choose a student at random with replacement and then ask the question. Okay, so I keep asking a question, but I keep repeating until everyone gets a chance. So some of you potentially might be asked twice or 3 times or so on, but that's just to make the question more relevant to the problem we saw just now. Okay, so I choose students at random with replacement and ask question. So if I have n students, how many questions should I ask in expectation? Okay, so I don't know if I should give time for this. It's pretty short, but maybe just a minute to fill in archipelago, just to ensure you've been paying attention. As we resume at 11:33. It's not a trick question, by the way, in case you're thinking it is. Okay, I think most of you probably knows like what it is. Okay, so starting to get random answers. Okay, never mind. So let's go on. So I hope you can see that this is exactly like a coupon collector, where the coupon in a sense is like the students, right? Like you guys. Then the collector choosing the coupon replacement is like me who's selecting one of you with replacement. Okay, so thus the expected question I have to ask is theta n log n. Okay, I see some randoms like log n, n squared, and n, but I hope like for those who chose it, you can see like how this maps to a coupon collector problem, like the one I spent like a few minutes explaining earlier just now. Okay, so pretty simple. So for the fourth question, it's about like querying. So I have an array, right, of distinct names, 1 to n. Then m of them are male. M of them are male, and I want q out of the m males. I don't care which q, but as long as I get q males, it's fine. So what the algorithm does in the pseudocode is that it just keeps choosing names until it has obtained q males. Okay, so you just keep choosing until you get q males. Okay, so for each iteration in the loop, you just check whether it's male or not, and if it's not, then you try again. Okay, then repeat it q times. So you want to count how many times in expectation you access this array A. Okay, line 5. So okay, so let me like maybe elaborate a little bit more in case like the m and q are confusing. So let's say I have 10 people, like in this class there's 25 of you, right? There's 25 of you. Let's say like there are 15 male and 10 female. Okay, then this is the m. The q is like I want a value q that is lower than m, or it can be equals to m. Maybe I want like 5. So as long as I choose 5 out of these 15 people, I'm happy. Okay, as long as this algorithm managed to find 5 of these 15 people, then I'm happy. Okay, so this is the question. Okay, so I don't need you to fill in archipelago, but I'll take the time to like, in case you have any questions, please ask me. Okay, maybe I'll give you a minute or two to think about it, but you don't have to fill in archipelago. Okay. Any questions? Is the question formulation okay? Like if that's okay, please give me a thumbs up. Okay. Ooh, starting to have like less and less thumbs up. Is it just like confusing, or do you need me to repeat anything for those who are not saying anything? Okay. No one's exactly saying anything. So, okay, I hope at least the question makes sense. Okay. And the answer for later is slightly more like mathematically involved. But if you follow the coupon collector analysis today, hopefully like this will be, you can follow this one as well, because it kind of requires a bit of coupon collector analysis. Okay, I'm gonna go on. Okay, I hope it's very familiar. As I said, like it's a coupon collector, but with a slight modification. In the actual coupon collector, the original coupon collector, you keep trying until you get n of them, like every single one of them, n of them. But this one is kind of like a coupon collector with early termination, where you stop if you have obtained Q coupons. Okay, so so think about it this way, like maybe the coupon is like the male students, right? And the collector choosing a coupon replacement is like this algorithm that I have accessing the array A. Okay, so let X be the total number of accesses. Okay, total number of accesses you have, then let Xj be the number of accesses to obtain J of male. Okay, this is kind of like the coupon collector formulation again, like finding the J of new male after you collected like J minus 1. Okay, that sounded weird, but after you have like selected J minus 1 male, after you've chosen J minus 1 distinct males, how many access do you need for the J of 1? But this time you stop until Q has been found. This is the only difference from the coupon collector problem. So let's derive it. Okay, so what's the probability of success? Okay, so finding first male is like there are m males out of n people. Finding the second male, well, you have n minus 1 left. So finding the J of male, if you follow the pattern, is simply m minus j minus 1 males out of the n people. Okay, this is just like deriving for in the general case, if we are choosing the J of male, how many males should there be left that I have not chosen? Okay, so xj is definitely a geometric distribution with the success probability of, well, this is m minus j plus 1, basically. It is the same thing over n, because I have n students in total, the male and female included. Okay, so expectation of xj, the expectation of xj is simply again the reciprocal, right? This is what we explained like earlier in the class. This is just the fact. Geometric distribution, the reciprocal is the expected value. Okay, so this is just flipping it together, n over m minus j plus 1. Just take the reciprocal. Okay, and now again, same as the coupon collector analysis, we apply linearity of expectations. First, we take x equals to summation of xj from 1 to q, right? Because we stop at q, take the expected value, break it up. Okay, yeah, just warning, math ahead. Okay, a lot of numbers. So this again is the linearity of expectation. I push the expectation in, and the expected value of the sum equals to the sum of the expectations. So push the expectation in by linear expectation. Okay, then recall the previous slide, we have calculated E of xj. Okay, we've calculated E of xj, and this is simply n over m minus j plus 1. This is what we have in the previous slide. So we replace it over here. Okay, and then notice how this is, if you expand it, this is like n over m plus n over m minus 1 plus all the way to m minus q plus 1. Okay, so this is just the expansion of this sum. Okay, this is where the math gets more like involved, or slightly more involved, I suppose. Okay, so look at this thing over here. Hopefully you can like kind of see these feel like a harmonic series, because in harmonic series, right, the denominator increases 1 by 1. Okay, or if you look at from right to left, it decreases 1 by 1. So here the denominator also decreases by 1 each time, but it stops early, right? So it's kind of like the upper half of the harmonic series, so to speak. Okay, so the trick here, right? The trick here is that because we did not start from this region, like these values are excluded, let's like artificially introduce it. Okay, and how do we do that? So we do this thing over here, and it looks very scary because there's a lot of new terms introduced. But this is just, well, take the same series over here, but then you do like you add some terms and then you immediately subtract it away. Okay, so it's like here 5 plus 4 plus 3 is just like all 5 plus 4 plus 3, then plus 2 plus 1, then minus 2 plus 1. Okay, so this slide is basically just demonstrating this thing. Okay, and the reason we want to do this is so that it looks like a harmonic series. We can actually apply the harmonic series directly. Okay, so the next step I do is I to factor out. Okay, I factor out the n, factor out from both the sums. Okay, then notice how both of them are now actually harmonic series, but one of it ends with m and the other one ends with m minus q. Okay, so harmonic series Hn, it ends with 1 over n, Then here it ends with 1 over m. Here it ends with 1 over m minus q. Okay, so this is what I did over here. So, well, hm is, as I mentioned earlier, if you look at harmonic series, just think of the logarithm of the highest denominator. So this is log m, and this is log m minus q. Okay, so theta n log m minus n log m minus q. Okay, this is just replacing the harmonic series. Then by logarithm rules, okay, if it's a minus, like logarithm minus another logarithm, then simply the result is a log of the fraction of in the inside here. Okay, so I bring the m as the numerator and m minus q as the denominator. Okay, so we get this bound over here. Okay, and the expected total number of excess is theta of n log m over m minus q. Okay, last semester I had a question like, hey, because this is a minus, right? Can I like just ignore it and say it's like n log m? Right? So, well, sure, like I think this is fine if this is a big O, right? So it's a big O because it's an upper bound, you take away this value, should be fine. Okay, but maybe in case like the prof like wants to be tight, right? Like let's say a recent assignment question, you want the answer to be tight, then maybe best not to throw away like too many values. Okay, so because like we maybe want to keep the theta, so we still consider this minus term and we'll apply logarithm laws over here. Okay, so yeah, actually that's all we have for today. Is a pretty short tutorial, but I know it can be math like involved. It's a lot of new concepts that was probably not taught in lecture, I think, except for the geometric distribution. But any questions for the derivation, or do you want me to repeat? Because like I'm done for today. I'm just gonna share the okay. I'm not done for today because I actually have an extra content in case like you guys want to stay back and hear me discuss some extra content. But I'm gonna share the slides in the Zoom chat. And so if you have any questions, please let me know now. But if there are no questions later on, like if you want to stay back, I will go through like some extra content, or we can start the consultation immediately. Okay, so is the coupon collector okay? Sorry, this final question about choosing M meals okay? Any questions? Can you give me a thumbs up if that's okay? If those of you who didn't thumbs up wants me to repeat some part, do PM me. I can do that. Okay, so no one's saying anything. This is, I think this is probably like the most chillax tutorial in 3230 in my opinion. So the future ones are not as chillax as this one, I feel. So okay, so all of you give thumbs up. I've received no PM so far. Maybe I'll just wait for like 15 more seconds. But if you guys like, I'll follow this with this additional analysis using indicator random variable section. And actually, I'll be releasing some supplementary notes for this, but this might be helpful for the next lecture. And actually, this is like a technique that we use a lot in randomized algorithm. Okay, so if you want to leave, that's fine. Class is officially over. What I'm going to go through now is just extra content, which I think should be helpful to analyze in 3230. Okay, so I'm just gonna begin. If you have any questions, PM me like usual. So just now we talked about random variables. So now we talk about a special case of random variables, which is the indicator random variables. Okay, the indicator RV is kind of like a counter, right? To count how many times an event happens. Okay, so let X be the indicator random variable where a certain event occurs with probability P. It is a 1 or 0 random variable. So typically, like people will say like, oh, it's an 01, 01 random variable. But I typically just say indicator random variable. So you observe that 0 or 1 is kind of like the way we count whether some event occurs. Okay, so if it did not occur, then we say the X is 0. Or if the event occurs, then we say it's 1. So it's to count like, hey, did you happen? Did you happen? Did you happen? Okay. So okay, now let's talk about expectation, because typically we like to talk about expectation in randomized algorithms analysis. Okay, So let X, right, be an indicator random variable with probability P of happening, right? So the event happens with probability P. The expected value of X, let's go back to the first principles. We use the formula. By the definition of expectation, we take 1 times the probability P plus 0 times 1 minus P. Okay, but notice how 0 times 1 minus P is, well, is 0. So this equals to P. Okay, what this implies, right, is that expected value of X is equals to the probability of the event happening. And this is actually very, very useful. It's simple enough, right? Because basically, if you can figure out what the probability of event happening is, you get the expectation for free. Okay, because P is the probability of it happening, and by the derivation we have here, expected value of X is simply the probability. Okay, and remember, this was the pattern that I talked about earlier, right? And in particular, I want you to like focus in this like part over here. I say here, calculate the relevant probability of all these x1, x2, and all the way to xn, right? And then the step B over here, I say is calculate the individual expectation. But in case your x1, x2 are indicator random variables, let's say they're IRV, by doing step A, you get step B for free. You get the expectation for free, because by definition of the expectation of indicator random variable, EX equals to the probability itself. Okay, this is why it's very, very useful to consider indicator random variables. Okay, so any questions so far? So I have several examples, but if you have any questions about what I said in the previous slides, let me know. Okay, let's see the 4 fair coins. Okay, so I think this example might be intuitive, right? So let's say we have 4 fair coins, right? I flip them one by one, right, independently. So what is the expected number of heads? Intuitively, you should know, like, I flip 4 fair coins, then half of them should appear head, half of them should appear tails. And that intuition is correct for here, because it tells you 2 should appear head. But let's try to use like the techniques we learned today. Okay, indicator random variable. So let xi be the indicator random variable for the event that the coin I, right, I have 4 fair coins, so coin 1, coin 2, coin 3, coin 4, it flips head. You get head out of it. So P equals to half. So that means like this is the probability that it becomes head. So let X, okay, be the random variable for the number of heads. So remember, this is the total random variable that I want to count. I want to count like how many heads are there in total. So I kind of like ask here one by one. Hey, coin 1, do you become head? Coin 2, do you become head? Coin 3, do you become head? Coin 4, do you become head? Something like that. So again, here intuition here is that each indicator random variable is kind of like a counter to count whether the event occurred or not. Okay, so you ask each one of these, the expected value of X, right, is simply E of X1 plus X2, X3 plus X4, like this one over here. So break it down by the linearity of expectation, and then each one of this is half. Okay, so here I just take the generalized form first. EX1, EX2, all of them are indicator random variables. Okay, and because of that, each of them is P plus P plus P plus P plus P. Okay, so well, because P is half, we know that 4 times half is 2. Okay, so this is the example 1A. So if we generalize to a fair coins, right, to n fair coins, well, you do a similar analysis as before, but with n coins and 4 heads, okay, you should get n over 2. Okay. Okay. So okay, nice. Let me see if I want to go through all these examples. Okay, maybe like something more exciting, right? Like I have n bias coin, right? N bias coin. So the probability is no longer uniform. Each coin has a different probability of success. So the IF coin has probability 1 over I of being heads. Okay, that means like I have n coins, right? Or four coins. The first one has probability 1 of being head, 1 over 1. The second one has probability 1 over 2, third one has probability 1 over 3, and the fourth one has probability 1 over 4. Okay, so this means this one is always head. The other one has like some probability of being head or not, but it's all different. Okay, so expected number of heads, well, in symptotic notation, if I go through it again, right? Okay, So let's go through it slowly. Again, EXI equals the 1 over I, right? This is by the question. Okay. So we formulate X as the sum of the indicator random variables. Okay. So we apply linearity of expectation. So push it in, right? Then we substitute. Here note that EXI equals to 1 over I. Okay. So this is 1 over I. And because like, again, today we talk about harmonic series. So I think it's appropriate that we do this. Okay. So this is simply another harmonic series ending with N. And so in expectation, we have theta log N coins being hits. Okay. I hope like from this example, you can kind of see like the power of indicator random variables and like how if you break it apart, like if you consider each case, and then like summing up everything, take the expected value of it, then break it out with like linear expectation, you get like some pretty like nice analysis. Okay, so yeah, I hope this section was useful. Because actually I think sometime in, okay, wait, my pen is stuck. I can't delete all these. Okay, ignore the annotation because for now I can't delete it. But sometime in this week's lecture, you'll see, I think this is from last time's slide because my tutorial happened after the lecture, but ours appear before the lecture. There'll be a slide that looks like this, I think, and it'll use like indicator random variables to analyze. So I hope like this section is useful for you for the upcoming lecture. Okay. I don't know why my pen is stuck, but maybe I'll stop sharing after this. So okay. So I'm not gonna go through the third example. I leave it to you to try. I have some other exercises to try like random variables if you like. We can talk about it in consultation also if you want. Yeah. So if that like I'll like officially stop here because it's 11:55. Don't wanna like keep everyone behind also in case you just FOMO or something. But yeah, thanks a lot for coming today, and for those who are like around, like thanks for staying back. And I hope this segment is particularly useful for this week's lecture and for the future analysis as well. Yeah. But thanks a lot. That's all I have today. If you have questions, you can stay back and ask. You guys have any questions? Most others have left. Seems like you guys stayed behind. Anyone? I have same question as the 3230 discussion group, which is, or I didn't really see the question. Oh, is it us discussing the where did 2C? Okay. Yeah, I think that's not probably very well explained. So okay, let me try to derive it on the spot. Because yeah, let me open up my notes. So I was actually like verifying that value as well. I'll put it in my iPad. So okay, so I'm gonna share screen from my iPad. Okay, so I'll just give the rough idea because I don't remember the full thing that was in the answer sheet, but the recurrence is Tn equals to T. This is assignment Okay, this is assignment 3, question 1C. I think the answer scheme. Okay, so the recurrence is this plus T, this is very thick, never mind, plus N, right? So this is the recurrence, and the inductive hypothesis is, Tk is less than equals to Ck for I less than 1, for 1K less than N, right? So this is the inductive hypothesis. So I'll just keep some steps, okay, just to give you the essence. So I want Tn, and this is upper bounded by Ck over 2. This is Cn over 2 plus C square root n plus n, right? So our goal is to get this upper bounded by Cn. Do you agree with me? So by some steps, we want this to be upper bounded by Cn. This goal, I'm not claiming this yet. This is the goal.
Yes.
Yep, because we want to show that inductive hypothesis holds, right? So this is the goal. Okay, so this is, okay, so make some observation. Let's take a look at this. This Cn over 2, right? Wouldn't it be nice if this was also upper bounded by Cn over 2? Because you add these two ups together, you get Cn.
Yes.
Make sense? But the question is this part over here upper bounded by Cn over 2? Okay, that's the question we want to answer here. And that's where the 2c over c minus 2 will eventually come from. So, so ask yourself, when does c square root n plus n upper bounded by Cn over 2 hold? Okay. Okay. At this point, I'm just winging it because I remember the steps are along these lines, but let's try. So what happened here? Let's multiply both sides by 2. Okay. Plus n. N. Okay. So 2c. Okay, 2c square root n upper bounded by. Let me know if you think I made a mistake anywhere, okay? Oh, okay. So, okay, wait. So again, I'll repeat, right? So we know Cn over 2 plus this thing. Ideally, we want everything to be upper bound by Cn. So would it be nice that this is already upper bound by Cn over 2? So that brings the question, when does this part upper bounded by Cn over 2? Okay, so I'm going to start from here, right? I'm going to start from here. Then I go to the next step by multiply by 2. So multiply by 2. This one, I'm just moving n over to this side. So I get c minus 1n. The next step I'm going to make is I'm going to make 2c over c minus 1. Right? This is just bringing c minus 1 down. Then upper bounded by n over square root n. Okay. So next step, well, this is just to keep some step. This is square root n, right? So then basically, like you see, what we have here is 2c, c minus 1 less than square root n. So we take power to both sides, and we get 2c over c minus 1 powered less than n. So what this is saying is that this thing holds, this value holds if you take the value c, do this manipulation, square it, and it becomes less than equals to n. So you deliberately choose a c such that if you make the choice of c, then you get by this like fraction, you square it, it becomes less than equals to n. So that's how like the fraction came about. Like, okay, I saw you put c minus 2. So is it c minus 2 or c minus 1? Did I do something wrong with my math here? Yeah, it's c minus 2. Okay, let me go back a bit to my derivation last time. Okay. Sorry. I made a mistake. It is c minus 2 because when you multiply by 2, there should be a 2n here. Yeah, my bad.
Oh, okay.
Yeah. So this is c minus 2, this is c minus 2, c minus 2, c minus 2. Okay, so crisis averted.
Oh, so since they chose C to be 4, so there'll be 8 over.
No, they didn't choose C to be 4. They chose C such that, if I'm not wrong, they chose A. Is it they? Okay, let me take a look at the argument again.
Oh wait, they didn't choose.
No, they didn't. They chose C that is large enough such that 2C. Okay, so from here, right, they chose 2C over C minus 2. They want it such that this squared is less than equals to 5. Okay, choose C. And the reason they want to do this is so that this guy over here holds. Okay, because remember, they chose, wait. So they covered cases where the base, their base, like double quote base, is for n less than equals to 4, right? So the non-base case is for n, then the non-base case is for n greater equals to 5, right? So as long as this value holds, right? This value holds for less than equals to 5, then as for your choice of C, as long as the choice of C squared is less than equals to 5, then this also implies that this is less than equals to n. Well, for n equals to 5 lah. Make sense?
Yeah.
Right? So as long as you are able to choose C such that this value holds, 2C over C minus 2 squared is less than equals to 5, it holds, then you satisfy that this is true for all the value n greater than 5. And because this is true for n greater than 5, right? Because of your choice of C, then this thing holds, right? Because this is like an if and only if, right?
Yeah.
So because the original thing holds, because this original thing holds, okay, then this is upper bounded by Cn over 2, which combining with this gives you upper bounded by Cn.
Wow.
Does that make sense?
Yeah.
Yeah, I was also equally confused when I saw it for the first time, like this thing, right? Like how come they get this term over here? It was barely explained, but yeah, I think the motivation comes from trying to upper bound this.
That's a very interesting approach.
Yeah, I thought so too. Okay, makes sense?
Yeah. Okay, thank you so much.
No problem. I guess I'll share this later to the discussion group as well, since people are discussing about it, right?
Yeah.
Can. Okay.
Bye.
Bye-bye. Okay, so thanks a lot for coming today. And if you're watching the tutorial, then thanks a lot. So yeah, I'll stop recording here.